Hello. Okay, so in this video, we're going to show that the set of real numbers is uncountable, that there's no bijection between natural numbers and the real numbers. I think this argument is very beautiful. I think it's very insightful, and I think you'll enjoy it. So let's jump right in. Okay. All right, so the first thing I'm going to note is that real number and the interval from 0 to 1 is the same cardinality. We can use the bijection of the tangent function. So what we could do is, so if we take a number between 0 and 1, not including the endpoints, and then subtract 1/2 from it, then we have an interval from -1/2 to +1/2. If we scale that up by multiplying by pi, then you would go from -pi/2 to +pi/2, not including the endpoints. And then if you take the tangent function of that, we will hit every real number between -infinity to +infinity. And this is injective because it's strictly increasing function. So that means that we found a bijection between the interval through real numbers. They have the same size, even though this looks like a finite length set, and this is an infinite length set. The number of different elements in there is exactly the same. Okay, so let's show that this guy, even this finite interval between 0 and 1 already is uncountable. Okay, we're gonna do this by contradiction. So we first suppose that there's a bijection between natural number and all the numbers between 0 and 1. And then what we're gonna do is we're gonna make a grid of digits. So any number between 0 and 1 could be written as 0.235716092 and like some infinite sequence of decimal expansion. So this is the first, whatever 1 gets mapped to. So this is the real number that it gets mapped to. And then 2 and 3 and so on. So if this is a bijection, this is a list of all possible real numbers between 0 and 1. And what we could do is we could show that this thing is not surjective if I could come up with a number between 0 and 1 that is nowhere on this infinite list of numbers. So what I could do is I could come up with a number using the list F that we see above here. So we're going to come up with this number X, and the decimal expansion is only going to have 1 or 2 as a digit. So I could use all the numbers, all the digits between 0 through 9 in this decimal expansion. But I'm only going to use 2 digits. And the rule is simple. Most of the time, I'm going to pick 1. So what I'm going to do is focus on this set of decimal digits. So I care about the first digit of the first number, or the second digit of the second number, or the third digit of the third number, and so on. So as long as these digit is not equal to 1, I'm going to use the digit 1. If there happens to be a 1 in this diagonal, I'm going to choose 2 as the digit. So, and I'm going to put together a number using this decimal expansion. So all of these numbers are either 1 or 2. Okay. And because of the way we chose our 1s and 2s here, we chose it so that it does not match the diagonal element, right? If it's not equal to 1, I'm going to choose 1. And if it is equal to 1, I'm going to choose 2. So I could have chose lots of different numbers here, but all I'm doing is avoiding matching this diagonal digits. Okay, well, this guy has to be different from everything on the list because it differs with at least one of the digits with every single element. So, for example, it can't be the first real number because it has a different first digit. It can't be the second number because it differs in the second digit. The only way to be equal is if all the digits match, right? So it is not equal to any element on that list. Okay. So this means that F does not hit every real number because we were able to come up with a real number between 0 and 1 that skipped over, that wasn't on the list. Therefore, 0 to 1 was uncountable because it wasn't a bijection, right? It wasn't even a surjection. And bijection means it's both injection and surjection. This idea is called Cantor's diagonalization argument. It's so beautiful where like, okay, you provide me a list of every single member and I'm gonna give you something that does not agree with it. And I think it's really brilliant argument. Anyways, so this means that real number is uncountable either, right? If 0 to 1 is uncountable, real number set is even bigger than that. So it has a larger size than natural numbers. And in fact, you can kind of generalize this diagonalization argument. And you could do it in terms of power sets as well. So remember, power sets are a set of all subsets of a set. And you can use this argument. I think I'm not going to repeat it because it's very similar to this diagonalization argument. So see the textbook. But you could take any set. It could be finite or infinite. If you look at a power set, then it has to be larger than the set that you started with, even if it's infinite set. So you can actually come up with some set that's larger than real numbers as well. So all you have to do is look at the power set of real number, and then that will be bigger than real numbers. So it's a much bigger size of infinity, but you can come up with even larger size of infinity by looking at the power set of real numbers and so on. So you could have this infinitely many different sizes of infinity as well. I hope that made sense. It's kind of mind-blowing and hard to wrap your head around. But yeah, there's infinitely many different sizes for infinite. Okay. This is a theorem you should know, but I think I will not cover the proof in this class just because it's long. It is in the textbook, so if you don't want to skip over any material, please read it on your own. It is a little bit technical, but it is understandable. So here's here's a very useful tool you could use to compare sizes. So sometimes writing down bijection is difficult in some situations, but maybe you can come up with two injections. So if you want to compare the size of A and B, what we could do is you could take a set A and find an injection into B, but not necessarily a surjection. So all the elements in A maps to some elements in B that are different, but maybe not every element in B is hit by this function. So if you can find an injection in one way, and you can find another injection going the other way. So every element in B could map into A, to distinct elements of A, but not necessarily a surjection. If you can find injection going both ways, then there is a bijection that goes, that hits everything. That's injection as well as surjection at the same time. So there's a construction to do that. So that is a tool you can use. So what this means is that if you can find the injection from A into B, then that means that A is at most the size of B. So if you can find an injection into it, then whatever you mapped into is either the same size or larger. I hope that made sense. Okay. All right. One more thing that I'm gonna leave you with is this idea of continuum hypothesis. So this is a really natural question you might ask next. So we have just shown that real numbers are bigger than natural numbers. So it's very natural to ask, well, if countable set is the smallest type of infinity there is, and real number is bigger size of infinity, is there a size strictly in between natural numbers and real numbers? So we know that integers and rational numbers are all same size as the natural numbers. And in any kind of continuum interval, like from 0 to 1, has the same size as real numbers. Is there a size in between? And the very surprising answer here, I'm not going to prove it in this class. It's totally beyond the scope. But it's actually, it could be either way. So this question does not have an answer in the mathematical axioms that we have today. What I mean by that is that answer could be yes, and answer could be no, and there'd be no contradiction whatsoever with whatever else we can prove within mathematics. Sometimes these questions do not have answers, and I don't know, like it's mind-blowing to me that it seems like a concrete question, but you could have a model of mathematics where, yeah, the real numbers is the second smallest size of infinity, and you could prove things with that idea, or you could say that actually there's some size in between, and if there is a size in between, you can actually show that there's infinitely many sizes in between as well. So you could have a world in which it's a little bit messier, where there's lots of different sizes of infinity in between natural numbers and real numbers. Okay, so just so I'm perfectly being honest, what I mean that this is not settled under our usual axioms, and that's called Zermelo-Fraenkel set theory with axiom of choice, and usually denoted ZFC. So if you see the letters ZFC, that means the usual set theory that mathematicians use, including what's called the axiom of choice, which is a little bit controversial, so some mathematicians don't like it, but most mathematicians think axiom of choice is reasonable axiom. Okay, that's it for today. I hope you enjoyed it. On Thursday, we'll have our midterm, and that'll be the only thing that we're doing that day. So there won't be any more lectures for this week anyway. So good luck with that, and I'll see you guys later.